Okay, good morning, everyone. Let's start the second session of today. So my name is Aleksei Udovenko. I'm the session chair for this session. And the session is about symmetric cryptography, first part. And there will be 3 talks, 2 local and 1 pre-recorded talk. The first talk is titled GRIOC, a family of low latency PRFs and its applications to authenticated encryption. The paper is by Ravi Anand, Subhadip Banik, Andrea Caforio, Tatsuya Ishikawa, Takanori Zobe, Fukang Liu, Kazuhiko Minimatsu, Mostafizar Rahman, Kosei Sakamoto, and Kosei will give the talk. Please.
Okay, thank you for the introduction. Okay, so I will talk about our paper. So it's about the design of new low latency PRFs. So this is joint work with the many authors as shown in this slide. Okay, so let me first introduce the background and motivation of our works. So recently, a small delay primitive is desired for some applications, so such as automotive communications and industrial control network, memory encryption, and pointer authentication codes. To meet this demand, so several low latency primitives have been proposed for the last decades, so such as Prince, Kalma, Mantis, Orthros, Speedy, and so on. And these low latency primitives can be roughly categorized into 2 types. The first one is PRP, so invertible primitives, and the other one is PRF, non-invertible primitives. And Orthros is only primitives which can be categorized into the PRF. So in this work, so we focus on non-invertible primitives, PRF. So although PRF does not have its decryption procedure, so many famous mode operation can accept PRF, so such as CTR, CMAC, and GCM. And so in fact, so several invertible primitives do not consider the cost of the invertible operation, even though they have their decryption operation. So for example, so the decryption of Speedy takes a longer latency than its encryption. So regarding the block size and key size, so 3GPP said the low latency primitive with 256-bit blocks will be necessary for 5G and beyond 5G system in the future. And of course, so it should support 256-bit keys for the post-quantum security. However, so almost all proposed low latency primitives support only a 128 or 64-bit key with 128 64-bit blocks. So therefore, so our research question is, can we construct a PRF with a smaller delay than Orthros, supporting a 256-bit key and hopefully a 256-bit block? So as the answer of this question, so we propose low latency PRF GRIOCs. GRIOC have 2 variants. So the one variant is GRIOC 128, which supports 128-bit block with 256-bit keys. And the other variant is a GRIOC 256, which supports 256-bit blocks and 256-bit keys. And design of GRIOC is based on the multiple branch based structure like Orthros. But the difference from the Orthros is the GRIOC is based on sum of 3 keyed permutation. But so Orthros is based on the 2 keyed permutation. For the performance, so GRIOC 128-bit realizes a small delay than Orthros, and GRIOC 256 realizes a competitive small delay compared to other low latency primitives, even though which supports 256-bit keys. Okay, so let me explain the specification of GREOC. So this is the overview of the GREOC. So GREOC 128 has a block size 128 bit with a key size to 56 bits. And so GREOC 128 bit has a round reduced variant. So named so GREOC 128 dagger. So the number of round is 10 and 12. And also, so GREOC 256 supports block size 256 bit and key size also 256 bits. And so GREOC 256 is also has a variant of round reduced version. And the number of round is 16 and 12. For security claim, so GREOC 128 and GREOC 256 claims 256-bit security against the key recovery attacks in a single key setting. For GREOC, the reduced version of the GREOC, so they claim the same security, 256-bit security against the key recovery attacks, but the available data complexity is limited to up to 264 and to the power of 64 and to the power of 128. Okay, so let's look. So this here is the detailed specification of the underlying computations. So the underlying computation is based on the substitution computation network. So consisting of S theta pi and so other round key and other round constant operations. So S is a parallel application of S boxes. So in GREOC, so we use different S boxes depending on the branches. So in branch 1 and branch 2, so we use 3-bit S box and 5-bit S boxes. But so in branch 3, so we use 4-bit S boxes, so which is the same S box used in the Ultros. The next, so theta is a 3-bit XOR, so as expressed by this formula. And so the parameter is parameters are depending on the branches and the variant. And pi is a bit computation, so which is also as expressed by this formula. And so the parameters are also specified by the depending on the branches and variants. And so the round key is so explains the round keys. For GREOC 128-bit, for GREOC 128, so the 256-bit key is first divided into two 128-bit keys in different way, depending on the branches. And for GREOC 256, the master key is used as a round keys by application of the permutations. So for more details key schedule, so please see our paper. Also. And lastly, so around constant. So we use the decimal part of pi as a round constant. Okay, so from this slide, so I'll explain the design rationale of GREOC. So firstly, so we have to consider so how we can construct the low latency PRF. So of course, so to this end, so the most we need to minimize the critical path of circuit. And the natural way is to do this is to reduce the number of rounds as much as possible. However, so it brings a problem on security. So it is hard to ensure enough security by the small number of rounds. So particularly for low latency primitives, so the differential attack is the main threat. So in fact, Speedy 7192 and Mantis 5 are broken by the differential attacks. And the best attack to Prince is also differential attacks. Therefore, so our main objective is to build a strong keyed computation against differential attacks. So to this end, so we employ the sum of keyed permutation-based construction, so like Ultros. So Ultros is based on the sum of two keyed permutation. And so the advantage of this construction is so it can provide a strong security against differential attacks. But the downside of this construction is so the algebraic degree does not increasing by the sum of permutations. So because so the whole entire algebraic degree is reduced to the maximum degree among the branches. So to remove this downside, so we adopt one more key permutation that has strong resistance against algebraic degree-based attacks. So as you can see by this figure, so we design branch 1, branch 2 to have a strong security against differential and linear attacks, and we design branch 3 to have a strong security against the algebraic degree-based attacks. Okay, so here, so in this slide, so I'll explain the difference of the design procedure of Orthoros. So in Orthoros, so the designer first design a low latency 4-bit SBox, and then they explore the nibble permutations with the designed SBox and almost immediate matrix by a nibble level optimization regarding the security of differential attacks. However, so in our design, so we first select the candidates of an SBox, and not so specify the first one SBox. And then so we explore the good combination of the SBoxes and linear operations by bit level optimization regarding the differential cryptanalysis. Okay, so how can we select the SBox? So we select the 3 and 5-bit SBoxes based on Chi operation, so which is very popular operation used in the ASCON and KEJAC, and the 4-bit SBox in Orthoros. And so we also examine the 3-way of parallel application of SBoxes. The first one, so phi 0 is just first one, phi is 32 4-bit SBox application in parallel. Phi 1 is 41 3-bit application with 1 5-bit SBox. And phi 2 is applied 3-bit SBox and 5-bit SBox alternately. So then, so linear layer. So we employ subterranean-based linear layer. So consisting of pi and theta. So theta operation is 3-bit XOR. So the number of candidates of the theta operation is 128 combination of 3 and 256 combination of 3 for 128 and 256-bit variants respectively. And pi operation is a bit permutation. And the number of candidates of the pi operation is 64 and 128 for each variant. So employing the theta and pi instead of normal bit permutation and almost immediate matrix is to increase flexibility in choosing the parameter of the theta operation. So which contributes to efficiently decreasing the DCP max on the parameter depending on the parameter. And so moreover, so the delay of this round function is almost the same as the round function of the Orthoros. So because 3-bit XOR, the latency of the 3-bit XOR is almost the same as that of the immediate matrix, almost immediate matrix, and bit permutation almost immediate matrix. And then so we explore the best combination of SBoxes and linear layers. However, so there are too many candidates of an SBox, combinations of an SBox and linear layers to evaluate the bit level optimization regarding the differential cryptanalysis. Therefore, so we employ a 2-step evaluation process, which is a very common process to design symmetric key primitives. So firstly, so we evaluate the diffusion property. And then, so we evaluate the security against the differential characteristics regarding the candidates passing the step 1. Okay, so in step 1, so we evaluate the full diffusion round, so which is the minimum number of the rounds that each input bit can influence all output bits. And so this table at the left side of this table shows the result of our result of the step 1, but so it's but there's still too many candidates. So we further look at the minimum number of bits influenced by each input before half or one round of the full division round. And so as a result, so this number of candidates pass the step 1. Then we evaluate the security against differential attacks regarding the candidates passing step 1. Oh, so this slide is so busy. So in short, so we found the candidates in class of phi2 is the best regarding the security against the differential cryptanalysis for both 128-bit and 256-bit variants. So we decide to employ the candidates of phi2 as a branch 1 and branch 2 to resist differential attacks in both Greyhawk 128 and Greyhawk 256. And lastly, so we need to design the branch 3, so we should good resistance against algebraic degree-based attacks. So to this end, so we use the candidates in the class of phi0. So because phi0 has a degree 3, while phi1 and phi2 has a degree 2. And so it should be mentioned that the phi0 does not have the best resistance, best security, the strongest security against the differential cryptanalysis, but so it also have a good security against the differential cryptanalysis. Okay, so I will explain the security evaluation against several attacks. So firstly, so here's about the differential and linear attacks. So as you can see in this table, so for Greyhawk 128, so Greyhawk 128 is secure at the 5. So sorry, so I can see. So yes, so as you can see in this table, so the Greyhawk 128 and Greyhawk 256 is enough security margin against the differential cryptanalysis. And next, so it's about integral attacks. So we evaluate the security against integral attacks by the division property. And so this attack is a kind of the algebraic degree-based attacks. So we need to carefully evaluate this type of security. So as you can see in the table, so for both Greyhawk 128 and Greyhawk 256, branch 1 and branch 2 does not offer good security against the integral attacks. However, so branch 3 can offer the good resistance against this type of attacks. And so, as I said before, so the entire Greyhawks, so the degree of the entire Greyhawks is reduced to the maximum degree among the branches. So the Greyhawk 128 and Greyhawk 260-bit has the same security as their branch 3. And so this slide shows the attacks. And yes, so we did a lot of evaluations. Lastly, so I'll briefly introduce hardware implementation result. So for environment, so we evaluate the fully unrolled circuit. And so we try two compile options. The first one, F1, in F1, so each CHES box is separately compiled by the compile ultra direction and then recompiled the entire cipher. And in F2, the entire block cipher is compiled by the compiled ultra directive. And as a result, so in many cases, so F1 is better when you want to optimize the latency, and F2 is better so when you want to optimize the area. So this is the details of the result. So as you can see in this table, so Grok 128 offers a good security. Grok 128 achieves almost the same latency as Orthoros. And Grok 256 realizes competitive latency compared to the other low latency primitives. So even though it supports 256-bit keys. And finally, so as application to low latency authenticated encryption, so we implement low latency. We offer a low latency variant of GCM dedicated to short input. So this is used in Intel SGX memory encryption engine, and the different from the original GCM is how to make the tags. So in the different normal GCM, so G hash is used to generate the tag, but so in this variant of GCM, so IP hash is used instead of G hash. So we implement IP adjusted for Grok. So this is implementation results. So adjusted IP is achieved a very good latency compared to normal AES-based IP hash. Okay, so this is summary of my talk. So that's the end of my talk. Thank you.
Thank you for your talk. Are there any questions?
Yeah, thanks for the wonderful talk. I just wanted to know, how did you land up to this particular diffusion function?
Sorry, so I can't hear you. So
how did you choose this diffusion function, the 3-bit diffusion? So did you search for, like, why didn't you choose for 5-bit or any other option? So why particular that function you choose for?
So you mean how to evaluate the diffusion property?
Before that, so you have x goes to x plus x,
X plus X.
t0 plus x t1.
T1. So okay. So
The 3-bit function.
yes, yes. So we tried every combination of these parameters. Does that answer you?
No, before that, where I was giving a specification.
Okay. Sorry. So please see our paper.
Okay, maybe we'll take this offline. Okay, thank you.
Are there any more questions? I have a quick question. So you mentioned the hardware, so it's designed for hardware. How about software performance?
I think so. Software performance is not so good. So because as you can see, we use many bit operations, and so the specification of Grok is quite complex. So maybe it's difficult to implement software efficiently, I think.
Okay, thank you. And let's just thank the speaker again, and let's move to the next talk. And the next talk is titled Compact Circuits for Efficient Members Transform. And the paper is by Subhadeep Banik and Francesco Regazzoni. And Subhadeep will give the talk.
Thank you for the introduction. Today I'm going to talk about compact circuits for Mobius transforms. So let me very quickly try and present the problem that I'm trying to solve. So we are given m Boolean polynomials P1 to Pm, each of n variables, let's say over GF2, with the added condition that each polynomial is, the algebraic degree of each polynomial is bound by some small constant d. The task is to find the common root of this equation system. Or in other words, the task is to find the vector r over n bits such that pi of r evaluates to 0 for all I. Such problems arise quite often in cryptographic contexts. For example, LowMC is a block cipher that has very low multiplicative complexity. It uses a degree 2s box. So the cryptanalysis of 4-round LowMC using a single plaintext and ciphertext pair amounts to solving a system of equations of degree 4. Furthermore, it's also known that cryptanalysis of digital signature schemes like EOV and their variants can be done by solving a system of quadratic equations. Now, if the system is linear, then it is not difficult to solve in a computational sense because it can be solved in polynomial time using Gaussian elimination. When the degree becomes higher than 1, then it becomes difficult to solve computationally. And in fact, it can be proven that the system is NP complete. Now, one way to solve such systems is by constructing truth tables. In other words, we evaluate each polynomial over all the points of its input domain. So in this toy example, we have taken m polynomials that are of 3 variables each, and we construct truth tables that we evaluate these polynomials at each of the 8 points of its input domain. And in this example, at the point 1, 0, 0, all the truth tables evaluate to 0. Or in other words, the OR function evaluated over the polynomials P0 to Pm also evaluates to 0 at the point 1, 0, 0. So for this toy example, 1, 0, 0 is the root. So this is what we are going to do for the rest of the talk. We are going to look at how to construct circuits that convert algebraic expressions of Boolean functions into their truth tables efficiently. And the way we are going to do it is by utilizing this algorithm called Mobius transform, which is a very efficient way of converting algebraic expressions of Boolean functions into their truth table. Okay, let me show you a picture of how a Mobius transform looks like. So the yellow column of bits in the left is called the algebraic normal form, or the ANF. So it is the Boolean representation of the algebraic expression of a function as a Boolean vector. For example, so in this toy example, I've taken the function 1 plus x0, x1 plus x2 plus x0, x2. The fact that x0, x1 is present in this function is indicated by the fact that the 110th bit, or the 6th bit in this yellow vector, is 1, which is the standard lexicographic ordering. And the yellow column of bits to the rightmost extreme is your truth table. Now you can see that the operation is completely linear. So there are n stages. Each stage has to the n minus 1 XOR gates. And the XOR gates are arranged in a fashion that is reminiscent of a butterfly circuit in the FFT algorithm. So in the previous slide, we just saw that all the operations are linear. So it stands to reason that the ANF vector and the truth table are related by some kind of matrix multiplication. And this matrix is called the Mobius matrix, or the matrix Mn. The ijth element of this matrix can be defined using this expression. And this matrix has been well studied in literature. I mean, it is known that it's lower triangular. It is known that it's involutive. Furthermore, much like the Hadamard matrix, you can use tensor multiplication to define the matrix Mn recursively. So back to the circuit. Now it's very easy to design exponential size circuits for Mobius transform. For example, you can simply stack these butterfly stages one after the other and make a huge combinatorial circuit that uses the order n times to the power n gates, but computes the transform in a single clock cycle. Now, this is possible, but this becomes infeasible as n increases because the size is exponential. Fortunately, there do exist polynomial size circuits to compute Mobius transform. And before we come to such circuits, let's look at degree bound functions. We know that the ANF of linear functions can have at most n+1 non-zero coefficients, because one for each variable and one for the constant term. Similarly, the ANF of quadratic equations can have a further n+2 non-zero coefficients, one for each of the quadratic terms. And similarly, degree D function, the ANF has maximum of the sum of n⁻I, where I ranges from 0 to t, which is the term that is upper bounded by n⁻d. So for small d, the size of the ANF vector is certainly polynomial in n. So now what can we do with this information? Let's go back to the circuit for a moment. We can see that after the first stage, the ANF vector is broken up into two vectors, let's call them A top and A bottom, of roughly equal size. And the circuit is essentially the application of Mobius transform recursively on A top and A bottom. That's how the circuit transform works. In fact, it can be shown that A top is the algebraic or the ANF of a Boolean function of an n-1 variable Boolean function in which the first variable of f has been set to 0. Similarly, A bottom is the ANF of the n-1 variable Boolean function where the first variable has been set to 1. And similar observations apply about each stage. For example, after the second stage, the top vector is an n-2 variable Boolean function in which the first two variables have been set to 0 and 0. The next one is 0 and 1, 1, 0, 1, 1, and so on and so forth. So having this information in place, we are now ready to define the recursive version of the Mobius transform, which first appeared in this paper by Dino. So at the lowest level of recursion, when you have reduced the number of variables to d by setting the first n-d variables to either 0 and 1, you can use the exponential size brute force Mobius circuit to simply fish out the truth table one by one. If not, what you have to do is to declare the array T for a Boolean function of one less variable, compute the vector A top, compute the vector A bottom, and recursively call the Mobius transform first on A top and then on A bottom. Now, notionally, this results in a recursion tree that you have to traverse in a depth-first manner along this orange line to compute the entire transform. Now, this is tricky even in software because each downward dive into the tree requires a context, a context switch. In other words, you have to save the local state information in some memory, which takes time and energy. So in software, this is quite tricky, and therefore in hardware, it's quite non-trivial how to map this in hardware. So if possible, so what would mapping into hardware of such an algorithm look like? So we have registers of decreasing size, one for each level, and which are connected by multiplexers and butterfly circuits. And we have the exponential Mobius transform circuit attached to the lowest most level. This is for the base case of the recursion. So now let's see. The topmost register will, of course, store the original Boolean function of n variables. But the level 2 register the size is big enough to store the n-1 variable Boolean function. But there are two n-1 variable Boolean functions. You have A top and then A bottom. So what this means is, before overwriting this second level vector from A top to A bottom, we have to finish the computation of the entire subtree rooted at A top before we can overwrite it with A bottom. And this is where the engineering challenge comes in. The engineering challenge is as follows: how to construct these multiplexer signals S0, S1, etc., so that at each node of the recursion tree, one is efficiently able to compute the left subtree first, then overwrite with the right subtree and do the computation of the right subtree in place. Yeah. So as you see that each recursion tree has two arms, and at level I, in one of the arms, one of the variables is set to 0. So in the left arm, one of the variables set to 0, and the right arm, one of the variables set to 1. So with this in mind, let us develop some notation. We abandon the notation A top and A bottom and adopt a slightly more complicated notation. Like at the ith level, we introduce the notation A depth of suffix, where the value in the parentheses is simply the depth from the top of the tree. And the suffix is an n minus d bit string, which denotes what variables we have set in order to get to that point. Or if you have not set any variable, we simply keep it at 0. So this kind of notation will be helpful in the arithmetic that we are going to do. Okay. Sorry. Okay, so we've seen that each node has two arms. In the left arm, because of the notations that we've used, the suffix actually remains the same. And in the right arm, because we set one of the variables to 1, the suffix actually increases by some constant, which is a power of 2. This is true for every node of this tree. In the left arm, the suffix remains the same. In the right arm, it increases by some constant. So, so imagine for a moment that at some time t, at the nth level, the ANF vector stored is AL of b, where b is an n minus d bit string, or equivalently an integer between 0 to n minus d minus 1. If the intermediate Mach signal is 0, let's say we want to store the left arm, the left arm of the recursion tree into the next level register. In that case, the suffix at time t plus 1 that is stored into the next level register is simply b. And if the signal Mach signal is 1, then let's say we want to store the right arm onto the next level. In that case, the suffix increases by this constant 2u minus l. And we can combine these two to get an expression for the suffix in terms of the multiplexer signal. Now, what did we achieve by this complicated expression for the suffix? So at the beginning, when I was trying to design the circuit, I was trying to see if I can engineer the multiplexer signals by hand so that the circuit works. So I took small values of n and d, like n equal to 5 and d equal to 2, and tried to find the values of the multiplexer signals by hand. That would enable that over 8 clock intervals, that is 2 to the power n minus d over here, over 8 clock intervals, the suffixes at the lowermost level of this suffix at the lowermost level is every possible bit string of n minus d bits. And if we can achieve that, then the circuit is guaranteed to work. Why? Because in essence, what we have done is divide the bigger Boolean function into 8 small component functions, and in each clock cycle, we get the partial truth table in 8 installments, one after the other. Now, so in this, we converted the simulation diagram that we just saw before into a table in which tabulates the values of, which tabulates the expressions of the suffix as a function of the multiplexer signals for each of the levels over the 8 clock intervals. Now, for the circuit to work, the leftmost or the rightmost column, which represents the lowermost level, that must equate to equate from 0 to 7. So we've basically reduced the problem of circuit construction into solving an instance of integer equations by limiting the solution set to 0 and 1. And if you were to equate it to the rightmost column to 0 and 1, to 0 to 7, and solve this equation system, you'll get exactly the multiplexer signals that are in this diagram. Now, the idea is to not only solve the system for small n and d, but for arbitrary values of n and d. That can be done similarly. So you just have to make expressions for the suffix at the lowermost level over 2 to the power u where u is n minus d, over choose the bar u clock intervals, and solve this set of equations over the integers, of course, by limiting the solution to only 0 and 1. So there are three pieces to this puzzle. The first is to show that the equation system has a solution. Now, that is not very difficult to see because the right side are all the u-bit integers, and the left side are expressions which resemble the binary expansion of a u-bit string. So the fact that the solution exists can be seen by, if you just assign each variable the expression obtained by the binary expansion of the right side. For example, 2u minus, observe the bottommost row, 2u minus 1 is the all one-bit string. So what you can do is assign each of the variables on the right the all one value. Similarly, the second last row, you can assign the all one every value 1 except the last variable you can assign 0, and so on and so forth. So the solution exists, it's easy to see. The next two parts of the puzzle are to prove that the solution is efficiently implementable. In other words, you can efficiently implement signals by using a limited amount of circuits. And the third part is to show that not only can you implement it with limited amount of circuits, but you can also implement it with circuits of logarithmic depth. Logarithmic in n, yes. So the second part is important because it allows you to have circuits of polynomial size. And the third part is important because if you can limit the depth to logarithmic in n, you can, what you essentially do is limit the critical part of the circuit, and then you can clock the circuit at higher and higher frequencies, which would be helpful if one of the applications that you want to use it for is solving equations. Okay, so I will not have time to go through the entire math. I would request you to find more details in the paper. But what we have done till now, we have proven that the circuit can be implemented with size polynomial in n and with depth logarithmic in n. Having this basic circuit in hand, now we designed 3 solvers. The first is very straightforward. We have, if there are m equations, we have m instances of the Mobius transform circuit. We OR the truth tables as we saw in the truth table example. And then we use some kind of a priority encoder to fish out the location of 0, of the first 0 in the truth table. So what this circuit will do, it will fish out the first root of every partial truth table. This will not, if there are multiple solutions per partial truth table, this kind of circuit is unable to fish out all the roots. But this kind of a circuit may be okay for certain applications. For example, this kind of a circuit can serve as a decisional oracle that tells you whether a system of equations has a solution or not. Of course, you can observe that this kind of circuit is very large critical path. The path shaded in red is completely combinatorial. So in order to reduce the critical path, we can use pipeline stages in between. Now, the third circuit, it's able to fish out all the roots by doing some more arithmetic. The idea is to stall the Mobius pipeline. If a partial truth table has multiple roots, then the idea is to stall the pipeline and to fish every root from the partial truth table one by one, at the same time flipping the corresponding location to 1. And we continue to do this till the partial truth table has become all ones. It doesn't have any more roots. And this is done with the combination of a priority encoder and a decoder. Of course, you will have observed that a Mobius transform circuit does a lot of redundant computation. It evaluates every Boolean polynomial over all points of its input space. And this is wasteful. So for example, imagine a situation where you have 50 equations and 50 variables, and let's say the common solution space of the first 10 equations is only 100. Then it is more judicious to evaluate the remaining 40 polynomials over only the 100 points of the common solution space of the first 10 polynomials, rather than execute the Mobius transform also on the remaining 40 polynomials, which would be equivalent to searching each of the 40 polynomials over all the 2 to the power 50 points of its input space. So in order to protect from this kind of wasteful computation, we propose a dot product-based circuit. So the first part of the circuit is expanding a root or expanding any input point R into a larger vector that includes the value of all the degree D monomials computed at this particular input point. And then if we call this expanded vector R, let's say, R in boldface. And now if V is the vector that describes the algebraic normal form of the function f, then f of R can be simply evaluated by doing the dot product R times V. Now, this is not only easy to verify, but if you think about it, this is how a normal human being computes a Boolean function. We actually compute this dot product in our head. So the combined circuit is as follows. We take, instead of m instances of the Mobius circuit, we only take mu instances of the Mobius circuit. Whatever common roots of the first mu Mobius circuits are, that are input into these m minus mu dot product circuits, and the root is declared valid if each of the m minus mu dot products also evaluates to 0. Okay, so we plotted the energy consumption as a function of mu, where the the dotted horizontal line represents energy consumption when no dot product circuits are used. So you can see that by varying the value of mu, we can more or less reduce the energy consumption by around 50%. So I'll conclude over here. So the conclusion is that we can make equation solvers using circuits of polynomial size and logarithmic depth, and using some additional linear algebra, it is possible to make the circuit more energy efficient. Of course, this is not all the optimizations that we do in the paper, and if you're interested, I request you to look at the paper. Thank you.
Thank you, Subhadeep. Are there any questions in the room?
So I'm just thinking from the practical point of view. So what is the feasibility of solving some system of equations? So you gave some example, let's say 50, right? So 50 variables, but typically, I mean, if we try to solve some quadratic equation or something for a particular cipher, so they are typically those the equation like number of variables. So
it's quite large, yeah.
Yeah, so that's quite large, right? So because hardware is already dedicated, right? So maybe FPGA might be an option, right? You know, to build something reconfigurable. So
yeah,
how is if you could comment on that.
So for that, you will need FPGA cluster, a cluster bit solution. A single FPGA device is unable to cater to very large number of variables. But using the fact that this kind of algorithm is parallelizable, right? For example, solving an equation system of n variables can be reduced to solving 2 to the power m parallel instances of solving a system of equations of n minus m variables, for example. So the parallelizability is inbuilt into this this kind of problem. So you can solve the original, you can break down the original instance into smaller sub-problems, right? And each smaller sub-problems you can solve in a different FPGA device. So if you are able to get access to a cluster, then it is possible to go up to 100 or 128 variables, even for quadratic equations. But going beyond that, I mean, it's possible. You just have to get access to a large enough cluster. And this is possible only because the system, the parallelizability is inbuilt into the system.
Are there any more questions? Okay, then let's thank Subhadeep again. And now we have the last session of the talk, which is pre-recorded. So let's enjoy the video. So The last talk of the session is an algebraic approach for evaluating random probing security with application to IS, and it is the authors are Vahid Shahindia Kaje, Bart Manning, Leila Batina, and Vahid will give the talk.
Hello, everyone. I am Vahid Jahandide, a PhD student at Radboud University in the Netherlands. And this is a video presentation of our work titled An Algebraic Approach for Evaluating Random Probing Security with Application to AES. Let's first start with defining random probing leakage model. Typical side channel attacks usually target a single sensitive variable, such as output of AND in this example. However, advanced attack can combine leakage of multiple variables. A natural extension in this direction would be considering leakage of all of the variables. And the random probing model is defined to get this notion. In this leakage model, each variable of the circuit that can be a protected circuit leaks independently with a fixed probability P. Our work considers protected circuits, and protection is usually achieved with masking. Masking is done in 3 steps. First, native inputs are n-shared. That is, if variable V is an input, it is replaced with a vector of values such as capital V, and these values are shares. They are chosen randomly such that their sum equals V. Gates are replaced with gadgets. Gadgets work on n-sharing. They accept n-sharing and produce n-sharings. To maintain security, a refresh gadget may be inserted at some of the interfaces. In general, the mask circuit will have more complexity compared to the original circuit, and one expects that this increasing complexity brings more security for native variables. To justify this expectation, we need to define a security metric. Assume native variable B is in the circuit and RPM leakage is provided to the adversary. Adversary's goal is to estimate value of V, and since it's always possible to estimate this variable by just randomly guessing it, we define advantage as follows. A circuit is considered RPM secure if advantage strictly decreases towards 0 by increasing masking order, given that leakage rate is limited to some threshold. Our main contribution is to estimate value of advantage for various gadgets and circuits. And this process answers to the sum of the open challenges in random probing model. We just briefly list these challenges. For typical mask circuit in the random probing model, security holds only if leakage rate decreases with masking order. This is shown for ISW gadgets in previous works. In some of the works, derived security band found requires leak-free refresh gadgets. And also, some of the previous results suggest that security bound is dependent to the complexity of the protected circuit. For instance, this bound implies that in an imaginary AES, if we increase the number of rounds, security of native variables will decrease. The state of the art for addressing RPM challenges is expansion method. It works by remasking a mask circuit. if we have circuit C, it first masks it as a typical approach by changing gates to gadgets. And again, in this protected circuit, masking is applied, and this continues. This process can create a secure circuit that can withstand constant leakage. However, the overall process adds too much to the complexity of the produced circuit. Our approach is to estimate value of advantage without introducing any other compilation approach. So, as a starting point, for linear circuit, we show that they act as an erasure channel, some parameter. That is, if protected circuit is linear and random probing model leakage is available, adversary will either directly require a circuit with some probability or will learn nothing about circuit. The metrics that are defined so far are related. So advantage and ESC, erasure channel parameter, are easily related. We deploy a Monte Carlo approach to estimate erasure channel parameter. Since circuit is linear, there is a matrix Pn that satisfies such system of equation where sigma C is the list of intermediates of the circuit. The rows of Pn are linearly independent, and if an attacker learns a leakage, it can substitute in the system and drive a new system. By finding a set of solutions, the adversary can estimate the value of V. So the system can be processed by computing row echelon form, and it transforms to the following system. Since this is in the finite field, it has a bounded amount of solutions. For this system, V is a pivot variable, and the system either uniquely determines V or gives no information about it. And the behavior is determined by the structure of the row containing V. And so it is independent of the realization of leakage. This enables to come up with a method for estimating value of ESC. That is, the probability that equation defining secret variable contains no free variable, and is proved in the paper that in this case, secret can be uniquely determined. However, computing this probability using analytical approach seems to be very difficult. Instead, we go for a Monte Carlo approach. A Monte Carlo approach can estimate probability of an event by repeating the experiment n times and recording the number of times that event occurs. In this case, the division like this will be the output for the probability. This figure depicts an example of obtaining value of ESC in the paper, and we see that as the number of trails increases, estimation quality improves. So instead of analytically obtaining a value of ESC, we repeat the whole procedure for many times. And after a while, we obtain a value of probability, we obtain the value of this probability with a decreasing amount of noise. Continuing this approach, we can obtain a table of values. However, this will limit applicability of the results. We made another observation, and we see that estimated value of ESC decreases exponentially with n. As an example in the paper, multiple gadgets, linear gadgets are cascaded, and they decay, and ESC for them is shown to be decreasing exponentially. So a formula like this fits most of the considered gadgets. This enables applicability of results in more complex structure. Going to more complex structures, we need other tools. We develop a composition theorem for computing RPM security of complex structures. In this example, SG1 is processing a native variable V, and output is fed to a refresh gadget, and its output will be fed into another gadget. For this composition, we show that the probability that adversary obtains native V from this structure can be bounded to 3 terms. One for this gadget, one for refresh, and one for the final gadget. They are separate, but the probability of the leakage is replaced with some bigger value. And this bigger value is a function of masking order and leakage rate, and also the structure of SR. Our main technique to obtain this result is to process parity relations inside refresh gadget. We have shown that parity relations inside refresh gadget can be grouped in 2 parts. One set contains intermediates and boundary variables, and the other set only contains boundary variables. Here, L1, L2, and L3 are linear relations, and P1 and P2 are constants. Equations in L1 are proved to be independent, and we have also shown in the paper that the upper system will give no knowledge to the adversary about variable V. So only lower system is informative, and to drive the bound, we will let the adversary to learn the remaining unknowns of the lower system. This is shown to be equivalent to some extra leakage on the input and output shares. For a refresh gadget, our numerical computation estimates the simple dependency with value of P' and P. A big circuit like AES, other than linear gadgets, will be composed of nonlinear gadgets as well. And the multiplication gadget is one example. A typical multiplication gadget can be decomposed to math-mult and comp. I mean, if an n-share inputs are coming in, math-mult will multiply them share by share, and this will be a n2 sharing for z. And then we need a compression algorithm to make it an n-sharing. We will use linearization approach to drive a lower bound and upper bound on adversaries' post-leakage information. Simply, we can use the comparison theorem of the previous slide and decompose the security of combination to the security of each gadget. MathMult itself is nonlinear, and the tools that we have developed so far are just for linear operation. So we need to study the structure of operations inside MathMult. For examples of the multiplication in paper, we see that operations inside it can be arranged as follows. And a final multiplication like EI equals to xi multiplied with yi are the only non-linear relations. So if we can get rid of them, we can use tools developed so far to obtain results. So if we ignore leakage of EI, nonlinear terms will disappear. This will reduce the advantage of adversary. Hence, the derived one will be denoted with E minus. We can also disclose value of xi and yi to the adversary, and it will give another bond that we denote with E plus. For some of the gadgets, for a specific gadget in the paper, we have shown that E plus and E minus are exponentially varying, and they are used in our suggested implementation for SBox and the whole AES. So we have considered more complex structures like as SBox of AES. Here it is a depiction. To use our theorem, we need to insert refresh gadgets and at all interfaces, and the structure uses 4 multiplication gadget. The bound derived uses the composition theorem, and it is clearly depend on the number of gadgets in the protected implementation. The paper also includes a section for analysis on the whole AES structure, and it is shown that the derived final bound does not depend on the number of gates in AES. So to conclude our talk, we defined the metric for RPN security and established a framework for evaluating it. We demonstrated how to handle leakage of refresh gadgets, and this gave us a composition theorem, which is inherent to random probing model. Our work provides a clear relation between circuit complexity and RPN security. However, the final numerical relations are derived with Monte Carlo estimations. An interesting follow-up work would be to analytically sketch these probabilities and verify the estimations. And this concludes my presentation, and thank you for your attention. I will be happy to receive your question via email.
Okay, let's thank Wahid for the recording. Could we connect by Zoom to the speaker? Wahid, can you hear us? Wahid, you're muted. He says he doesn't have a right to unmute himself. Can we please unmute him? Does work? Okay, then let's ask questions in the chat. Are there any questions to Wahid from the room? Yeah. Okay. Yeah. Oh. Okay, if there are no questions in the room, I have a quick question. Does your method, is it limited only to expansion-based protections for the random probing? You can answer in the chat and then I will read your reply. Okay, so Wahid replies that actually they use the method for normal compilations as well. Are there more questions in the room? Okay, well, he answers that they also compare the results with the expansion method, but their method is applicable to normal computations. Let's thank Wahid again, and let's finish the session and go to have lunch. Thank you.